So I'm going to introduce torque. It is called rotational analog of force. So why it is called so? Uh, just as force causes linear acceleration, torque causes angular acceleration. We know that all angular variables are analogous to they have a counterpart in the linear case. For example, corresponding to linear displacement x, we have angular displacement theta. Similarly, uh, theta corresponds to x. Similarly, angular velocity corresponds to uh, velocity. Similarly, mass corresponds to moment of inertia corresponds to mass. So there are several analogy between linear and angular variables. So in that continuation, torque is another example. So it is defined as torque denoted by letter tau, and it is defined as r cross p r cross f, r cross f. If we talk about its magnitude, obviously, as we know, for every vector product, magnitude is given by r into f into sine theta. This can be picturized as, suppose this is some point where some force is acting. Suppose the position vector of the point of application of force is F, and this is the force. The angle between the force and uh, the position vector is theta. So if I break the component of F into that along the position vector, that becomes r cos theta, and another component along, let me use a different color, perpendicular direction, that is f sine theta, f sine theta. Now the question is, what I mean to define is something which causes some corresponding to that force. uh, what is the rotational effect caused by that force actually? So we can see that this component r cos theta has no contribution in any kind of rotation. It is suppose this is point of axis of rotation. So if we consider this component, it has no role in rotating. But this component, if sine theta, has the only component which has some effect of rotation. So that's why we take only f sine theta. Further, in this product, there is also r. The question may also arise, why r is there? So we, from our observation, we can see that from our practical many examples in our everyday life, that if we apply, suppose a force here, and we apply a force here, and we apply a force here, we can see that this force will have most efficient this will be most efficient in causing the rotation. that is producing the angular acceleration, which we will see later. So this will have more effect. Why? And it is also the farthest one, that is, let me call it R1, this is F1, this is F2, and this is F3, and this is, let me call it R2, and this, let me call it R3. So we can see that F1, which is located at farthest point from the uh, axis of rotation, will have more effect of rotation as compared to other forces which are closer to the axis of rotation. And in particular, if force acts along at the axis of rotation, there will be no rotational effect. So that is the reason why here it is R as a product. Greater the R, more will be the effect of rotation. That will be later I will call it angular acceleration. So angular acceleration will be more if R is more and F is more. And the next question, why this theta? So again I would like to show that what is the effect of theta. Effect of theta. Again, let me draw. If force is acting like this, and another force is acting like this, yet another force is acting like this, we can see that this force F1 has no component along the perpendicular direction, and it is only perpendicular component of the force which is causing the rotation. So F1 has no component along perpendicular direction, F2 has little lesser component, theta 1, F2, and let me call theta 2, F3. So which force, if magnitude of all the forces are same, then obviously this force F3 has most effect of rotation, that is angular acceleration, because it has maximum component along the perpendicular direction which is causing the rotation. Again, let me repeat, the component in this picture also, the component along the radial along the position vector has no effect of rotation, and the component perpendicular only has the effect of rotation. So perpendicular component is obviously f sine theta, sine theta. So that's why this whole combination r into f into sine theta must account for something which is meant to cause rotation or produce angular acceleration. This is the reason. Now let me come to the mathematical expression for uh, torque in terms of cross product. We know that for any cross product we have A cross B is equal to, it is given by I, J, K. If vectors are given in um, component form, then it becomes Ax, Ay, Az, and Bx, By, and Bz. So applying to our definition of torque, I can write it as torque is equal to R cross F is equal to I, J, K, and the components of first vector, that is R, are simply X, Y, and Z, and the components of force are Fx, Fy, and Fz. Now we know how to expand it. So it is I uh, we let me repeat how to expand in this determinant form, how vector product is written if it is written in this determinant form. So it becomes we take first I and forget about this row and this column, and then cross multiply this like this. So y fz minus z fy. Then next step we take j and forget about j column and j row, and then I take the reverse order. In order to keep this positive sign, there are two ways. Either we take alternative plus minus, then we don't need to reverse the order, but I would prefer keep it plus and then reverse the order of multiplication. Initially I had multiplied like this and this. Okay, so this time I will multiply in reverse order. So it is z minus uh, this row and this column are forgotten, then xfz zfx minus fxz, and finally k. So instead of reversing the plus minus sign, I prefer to reverse the order of multiplication. So here k and then k row, this row and this column are forgotten, then I multiply in again in direct order x fy minus y fx. So this is the net this is the complete expression for torque in component form. So this is torque, and these are the components. I can write it as tau x. The component with I is obviously tau x. So tau x is y fz minus z fy. Tau y is z fx minus x fz, and tau z is x fy minus y fx. So these are the three components of obviously torque is a vector quantity because it is defined as a cross product of two vectors, so it's a vector quantity. Now let me come to the direction, how direction of torque is given. So like any cross product, direction is given by right hand thumb rule, which says that if I rotate a vector A through the smaller angle towards B, if I rotate the vector A towards B through the smaller angle between them, then the direction of thumb gives the direction of the vector product. So in this case, if I rotate like this, the direction of thumb will be out of the page. So I would denote like this out of the page. So in this case it is. So same thing applies to torque also. So torque is equal to R cross F. If direction of R and F are known, suppose first of all we have to join them tail to tail. After joining tail to tail, we rotate R towards F through the smaller angle between them, and then so again in this case the direction will be out of the page. Another example, if force is R is like this and force is like this, R and F. So in this case, so R cross F, if I apply right hand thumb rule, if you rotate R towards F through a smaller angle, then it will go into the page. So the direction of torque will be like this. So I would like to give some examples. Example. Suppose the force of force of 20 Newton acts at a point which is 10 meter away. Axis of rotation at an angle of 37 degree. Find torque. So magnitude of torque will be R into F into sine theta. R here is 10 meter into 20 Newton, and sine 37 degree is 3 by 5. So it becomes 5 to the 10. 120, and its unit is Newton meter. From definition it is clear that it is R and F, meter for R and Newton for force, and this is unitless, so its unit is Newton meter. One thing I would like to mention here, that there is a very frequent question in unit and dimension, that there are several quantities which are dimensionally same, but they are entirely different quantities. So one example is, most prominent example of that is torque and work. So dimension of torque is R into F into sine theta is equal to, for R we write L, and for force MLT minus 2, and this is dimensionless, so it becomes ML2T minus 2, which is same as the dimension of work, which can be checked. Work or potential energy or kinetic energy or heat, anything. So they all have same dimensions. Next, I would like to give there is something called couple. Whenever two equal and opposite forces are applied at an object which is fixed at some point, and we apply, suppose, force F1 like this and F2 like this, we can see that and equal, actually forces are equal, sorry. If two equal and opposite forces are applied at two ends of rod which is fixed at the middle, and let the distance between let me call it D, and this is also D. So we can say that here net force is 0, and net force 0 implies no translational motion. So in fact here the center of mass of the system is actually fixed, which is actually the center of the axis. So it is inconsistent with the fact that this implies no translation. But even in this case, there can be rotation. And why? Because rotation is caused by torque, and if we calculate torque, we can see that it is non-zero. So torque of this force is, let me calculate net torque. And first of all let me be assured about the direction. Let me talk about direction first. So direction of torque. So this torque, if I proceed it further, the direction of position vector of this force and the force, the angle between them is 90 degree, and if I calculate r cross f, it will be into the plane of the this page, into the plane of the page. Similarly, if I calculate this again here, if I this is the position vector, if I further proceed it little, then this will be the angle between, because in order to calculate the angle, in order to find the angle, we have to join the vector tail to tail. So here it is head to tail, so I have to proceed it little later. So it becomes uh, so if I calculate r cross f, then it becomes into the page. So both the torque caused by this and this are into the direction wise they are same. So if they are same, then we just forget about the direction and let me calculate the magnitude. And later I can say that they can be added. If direction are same, they can be simply added. So net torque is equal to tau 1 plus tau 2 is equal, because they are in the same direction, so I have simply added like a scalar. In fact, it's quite a general practice that whenever some a vector, two vectors are along the same line, then we can add them like a scalars, and keeping in mind that their directions are whatever the direction that is, we can keep separately in my mind. So tau net is equal to tau 1 plus tau 2, and that is simply d into f into sine 90 degree, again d into f into sine 90 degree, that is simply 2 into d into f, and 2 into d into f is nothing but 2 into d is simply r, distance between the forces. See, that is r into f, where r is the distance between forces or ends of the rod. So in this way we define what is called a couple.